Mr. Harry, Mr. Ryan, right?
Yes.
Okay, so last time we talked about this problem to finding a path in the binary tree with the given sum, right? And we use the depth search. Given this target t, we want to find out if there's a path from the root to the leaf node that the sum of the nodes visited is 9. Okay, so yes, we find it is 1 plus 2 plus 6. And then we can use the depth search. By visiting the nodes, we keep an updated value or we accumulate. Basically, there are two ways. We accumulate the sum when we visit the nodes, or we keep a remaining sum. Right? For example, accumulate sum 1 plus 2, 1 plus 2 plus 6, and then we find it. We find the target sum, and then it's a leaf node, then we find the path. Or we take out the value from the remaining sum. So we have 9, we take 1 out, which is 8 left. We take 2 out, 6 left. We take 6 out, 0 left. Okay? So let depth search, we're using the recursion. Right? Either we find the path in the left tree or we find the path in the right tree. So recursively calling the left and right. Okay, so what comes into your mind if we are not using the depth search?
Breadth search.
Well done, breadth search. Breadth search, level by level, right? Level by level. So just give me a second to find the eraser. Okay?
You wanna.
Okay, I'm back. So breadth search, level by level. So we should use the deque. What is a deque?
Double-ended.
So what does it mean by double-ended?
It has 2 ends.
Yeah, it means that the two ends we can push and pop in both sides. That's the
We're
double-ended
using
queue.
Q.
Look, this is a queue, eh?
DQ.
First in, first out, right? Queue. The first in, last out, what is it?
And first and last out is stack.
Stack, well done. Look, this is a stack, right? You put the thing in, you take it out last, right? Like a plate. You put a plate. When you take the plate out, you take the topmost, which is the last
So they
edge.
don't break.
That's right. And first in, first out, right? First in.
Doesn't break.
So this side, look, first in, first out, right? We in queue, we push the element to the queue on the right hand side. We take it out from the left hand side. It's just like when you're queuing for something, right? It's first in, first out, right? And we're using the double end queue because that the operation on both sides are all one constant. If you were using a list, a simple list like q equals something, then we can say q dot append 1, then you put 1. Q dot append 2, 2. Q dot append 3, 3. And we want to take that out in the list. We need to say q dot pop 0, right? 0 is the index, and that's the on linear term. But in a double ended queue, we use the q dot pop left. So if we don't specify the direction, right? If we say q dot pop, it's taken from the right hand side. Q dot pop left, taken on the left hand side. Q dot append, we in queue, we put the element, push the element on the right hand side. Q dot append left, we can push the element on the left hand side. Okay, so this is a very convenient utility class.
Yeah.
So breadth search 1, 2, 3, 4, 5. What's breadth search?
Level by level.
No, look, this is Q, right? Q. At the beginning, I put the 1 in, right? I put the 1 in. Now I visit it, and I take it out. When I take it out, deque means to take an element out of the queue. It means that I visit this. Yeah, we visit this 1, and then we push its kids 2 or 3 in. We can push the kids 1 by 1, or we can push all together. Okay, 2 and 3. Next element taking out from the queue is 2 or 3. The next element taking out from the queue is 2. 2, yeah, on the left hand side. So now what's the kit of 2?
4, 5.
Okay, I push it back to the queue. What's the next to take out?
3.
3. What's the kit of 3?
6, 7.
6, 7. Put it in. What's the next element to take out?
4, 5.
4. Okay, it doesn't have a kit, so we don't push anything back to the queue. 5, 6, 7. You see? So that's level by level, okay? So we want to find out if there's a path from the root to the leaf. So q equals deque. At the beginning, we put a root in, right? If no root, if we are given an empty tree, we should return true or false. If we are given, yes, false.
Yes.
So now look, while q, we can take 1 out or we can take everything out. It doesn't matter. Let's take 1 out. Okay, so current equal q dot pop left. If we want to take everything out, then we get the length of the cube. We get the number of the nodes in the cube, and then we can deque them one by one. Okay? So we take one out. Okay, so here we need to include the root and also the sum, remaining sum. Yeah, root and then remaining sum is target, right? With the tuple. So current node and then remaining sum s. So look, if s equal 0 and current left is none and current right is none. Can you tell me what's current left is none and current right is none? What does this mean? Return what? Look, current left is none.
True.
Yeah, why?
Just a hunch.
Current left is none. Current right is none. What does it mean?
It means if
Current is what node? This is current. This is node is current. This its left is nothing. Its right is nothing. So what's this node?
at least.
A leaf node. Okay, a leaf node. And it's a leaf node, and also the remaining sum is 0. So we should return true or false.
True.
True. Yeah, because we find the path and then it's a leaf node, right? That's what the definition is. Okay? Otherwise, then we need to keep pushing the kids. Yeah. If current dot left, then q dot append current dot left, and remaining sum is s minus current dot left dot value, right? And then if current dot right, q dot append current dot right, and then s minus current dot right, okay? Dot value. Okay. So if there is a left kit, we push the left node and then we deduct the value from the remaining sum. If there is a right node, we push the right node and the remaining sum, right? Remaining sum is that we take current dot right of value from the current remaining sum s. And then otherwise, if we don't find anything, we should return true or false here at the end, after the while loop. After we perform this breadth search, if we don't find a path here, so we should return true or false?
False.
False, easy. Okay, so this is breadth search. Yeah? Nothing special, right? The only thing we need to take care here is the remaining sum. Together with the node, we need to keep tracking of the remaining sum, right? Of course, we can do this with accumulate sum. So, you know the accumulate sum, right? Look, how do I change the accumulate sum? Here, is at the beginning we push the 0, right? Accumulate. And if s equal t, right? And then current value, I should change this minus to plus, right? Yeah? Make sense? Okay, so have you wondered that if I change this deque to stack, what happened? Everything stays the same, but this deque, first in first out, I change it to stack, what happened?
It won't work.
It will work because in this particular problem, the order of visiting the nodes does not matter, am I right?
Yes.
Does not matter because every node is visited once, right? The time and space complexity O(n). N is the number of nodes in the given binary tree. The space complexity O(n), because we're using the deque, right?
Yeah.
So if we change it to stack, what happened? Let me do this. Look at.
Depth search.
Whoa, yeah, that's a very good case. You become depth search. Remember, we talk about depth search. Usually, we're using the recursion to implement it. The computer maintains the stack for us, right? I have shown you, right? The breadth search, the order is level by level, right? Okay, so how about look here, right? Put the 1 in. Remember, I showed you 5 minutes ago with this, yeah? What's the next kit to take out? There's only 1, right? Okay, 1. What's its kit? Okay, you can push all the kits. Yeah, what's its kit?
2, 3.
2, 3. Okay, 2, 3. What's the kit to take out?
2.
Okay, remember this is a stack. When it's a queue, we take a 2 out. When it's a stack, we take which out?
3.
3. Yes, we take a 3 out. What's the kit of 3?
6, 7.
6, 7. We're gonna push it, yeah, we'll push it at the band. Okay, what's the next kit to take out if it's a stack? It's a kit. 7, yes. Take a 7 out. It doesn't have the kit. Okay, what's the next to take out?
6.
What's the next to take out?
2.
What's the kid of 2?
4, 5.
4, 5. Okay. What's the next kid to take out?
5.
And then 4, right?
Yes.
Okay, so what's this order? 1, 3, 7, 6, 2, 5, 4. Right? What's this order? 1, 7. So look. So note, right, left. Okay, so that's the reverse pre-order. Reverse pre-order, yeah? Remember the pre-order is note, left, right, okay? But how about if I push the right kid first, not the left kid? If we push the right kid first. Okay, let's try this exercise one more time, okay? Look. Okay, let me try this, okay? 1. We take 1 now, right? We push the right and left. Okay, so that's 3, 2, right? What's the next to take out? 2. What's the kid of 2? 5, 4, okay? 5, 4. What's the kid of 4? Taking out 4, nothing. Taking the 5, nothing. 3. Take it out. What's the kid of 3? 6, 7.
haven't written 5 though.
Okay. 6, 7. Then it's 7, 6. Yeah, we push the right key first. And then 6, 7. Okay, so what's this order? 1, 2, 4, 5, 3, 6, 7. 1, 2, 4, 5, 3, 6, 7.
Pre.
Yeah, pre-ordered. So it looks like default search, right? Alright? So look, magic. If you change the queue to stack, it becomes a default search. Right? Remember, we talk about default search, lots of different orders. Pre-order, in order, post order, reverse in order, reverse pre-order, reverse post order, right? Yeah? Make sense? Okay, so that's it. What have you learned today? Where's this lid? Okay, thank you. No.
It's nowhere.
Okay, everyone, what have you learned so far today?
About paths.
Okay, one by one. Alright, your turn. You go first. Remember, right? Come on, what have you...
So it's the same thing as we done last time.
Yes, and what's the problem? And what's the new today? What's the thing you learned today? Come on.
So we're doing the same thing, which is getting the most sum with ding dong.
It's not the most sum. It's the we want to find out. There's a path. Okay. Okay. Come on. Keep going.
If there's a path to the target.
Yeah.
And from the root to any leaf.
Leaf nodes. Yes. And then the algorithm we're using today is Traversal. And then this is the standard breakfast search. If we change this to stack, it becomes sort of. Okay, so let me define it. It becomes sort of depth search. Okay. Yeah. The time and space complexity is n is what's n?
The node.
The number of the node. N is the number.
Yeah, that's what I
okay.
said.
The node number. Okay. Right in your turn. What have you learned today?
The exact same thing we done
Last time?
yesterday.
Not yesterday. Okay. Then.
Well, last time.
Okay. What's the problem? What's the algorithm we're using today?
That we have a binary tree.
We have binary tree, and what are we doing with the binary tree?
Trying to try to add up the nodes to targets.
Yeah, we want to find out if it's a path from the root to the leaf node that adds up to the given target, okay? And then what's the algorithm we're using today?
Breadth search.
Okay, so by performing the breadth search, okay, so what's the second value in the tuple? What's this? We need to
target.
the remaining sum or accumulated sum, remember? Yeah? When we visit the node, we have to keep tracking of the remaining sum or the accumulated sum. Yeah, both ways. We can accumulate the sum and compare if it equals to the target, or we can use the remaining sum. Yeah, we visit the node, we take the sum, we take the value from the remaining sum until it reaches 0 in the leaf node. Alright? Okay, that's it for today. Bye bye.
Bye.
Bye bye.